Why all roads lead back to RDBMS. In the rapidly evolving landscape of database management systems, one constant has emerged. Despite the introduction of numerous new technologies and data models, relational database management systems have maintained their dominance. From the early hierarchical and network models to the rise of NoSQL and columnar databases, each innovation has not replaced but rather contributed to the evolution of RDBMS. This video explores the progression of various database technologies and examines why RDBMS continues to be the backbone of data management. It draws on insights from a recent academic paper, What Goes Around Comes Around, and Around, by Michael Stonebreaker and Andrew Pavlo, which offers a retrospective on several decades of database evolution. The journey of database technology began in the late 1960s with the introduction of hierarchical and network models, which laid the foundation for data organization and retrieval. However, these early models were soon eclipsed by the relational model introduced in the 1970s. Grounded in set theory and predicate logic, the relational model provided a more flexible and powerful method for data management. Over the decades, it has become the gold standard for database management, with SQL, structured query language, emerging as the primary interface. As data storage and processing demands increased, so did the search for alternatives to the relational model. This quest led to the emergence of various new data models and technologies, each promising to address the limitations of RDBMS. Yet despite their initial appeal, these technologies have either been absorbed into the RDBMS framework or have remained niche solutions, unable to supplant the relational model. MapReduce, popularized by Google in the early 2000s, was designed for large-scale data processing, particularly for unstructured data. It introduced a new approach to data processing, focusing on distributed computing across large clusters of machines. Hadoop, an open-source implementation of MapReduce, gained significant traction during the big data era. However, despite its early success, MapReduce-based systems faced criticism for their complexity and inefficiency compared to RDBMS. Over time, the limitations of MapReduce, particularly its lack of support for interactive queries and real-time processing, became apparent. Consequently, many organizations transitioned away from MapReduce, and today it is largely regarded as a legacy solution. Nevertheless, the concepts of scalability, elasticity, and fault tolerance introduced by MapReduce have influenced distributed RDBMS. Hadoop's limitations led to the development of other data processing platforms like Spark and Flink, which initially sought to improve MapReduce and later incorporated SQL support. As cloud computing gained prominence, these big data principles evolved and found new applications in cloud-based data lakes and data lakehouses. Key-value stores emerged as a solution for applications requiring simple, fast data access, often in a distributed environment. Databases like Amazon DynamoDB and Redis were designed to be highly scalable and efficient for specific use cases, such as caching and session management. While key-value stores offered significant performance advantages for certain workloads, they also presented limitations. The simplicity of their data model made complex queries difficult, and the absence of atomicity, consistency, isolation, durability, ACID transactions limited their applicability for many enterprise applications. Over time, some key-value stores have evolved to include more features such as support for semi-structured data, gradually bringing them closer to the functionality of RDBMS. Document databases such as MongoDB and Couchbase gained popularity in the 2000s as part of the broader NoSQL movement. These databases store data in a flexible, semi-structured format, typically using JSON or XML, appealing to developers seeking to avoid the rigidity of relational schemas. However, as with key-value stores, the initial excitement around document databases has diminished as their limitations have become evident. Many NoSQL databases have since added support for SQL-like query languages and ACID transactions, effectively transforming them into systems that closely resemble RDBMS. Concurrently, RDBMS vendors have incorporated support for JSON and XML data types, blurring the lines between document databases and relational databases. Column family databases, such as Google Bigtable and Apache Cassandra, were designed for large-scale distributed storage of sparse data. They are particularly well-suited for applications where data structures can vary significantly between records. Despite their specialized use cases, column family databases have remained niche solutions. They lack the flexibility and user-friendliness of relational databases. Similar to other NoSQL technologies, many column family databases have incorporated SQL-like features to broaden their appeal. While they play crucial roles in specific scenarios, they have not achieved the widespread adoption needed to challenge RDBMS dominance. The techniques of columnar data storage have been adapted for cloud-based data lakes and lakehouses, which use columnar file formats like Apache Parquet and ORC to store large data sets efficiently while providing quick query performance. Text search engines like Elasticsearch and Apache Solr, along with vector databases like Pinecone and Milvus, are designed to handle specific types of data and queries. Text search engines excel at indexing and searching large volumes of text, while vector databases are optimized for similarity searches in high-dimensional spaces, such as those used in machine learning applications. These specialized tools are invaluable for certain applications, but their narrow focus means they cannot replace RDBMS for general-purpose data management. Instead, they often function alongside relational databases in a polyglot persistence architecture, where different databases are used for different tasks. Following the mainstream popularity of large language models, LLMs like ChatGPT in late 2022, vector databases have gained prominence, with several RDBMS quickly introducing vector search extensions. Recent advancements in artificial intelligence, AI, particularly in large language models like ChatGPT, are significantly influencing the evolution of database technologies. These AI-driven tools are reshaping how databases are queried, optimized, and integrated into broader technological ecosystems. One of the most significant impacts is the resurgence of natural language interfaces for querying databases. Tools like ChatGPT have demonstrated the feasibility of translating natural language queries into SQL or other query languages with a high degree of accuracy. This capability could simplify database interaction for non-technical users, reducing the need for specialized knowledge in SQL or database schema design. While natural language interfaces have been explored in the past, the precision and usability provided by modern LLMs are unprecedented, potentially opening up new use cases for databases and customer service, automated reporting, and data analysis. However, while LLMs like ChatGPT can simplify query generation, they are unlikely to replace SQL or other query languages for more complex operations. Natural language queries can be imprecise, leading to ambiguities that may cause inefficiencies or errors in data retrieval. Therefore, AI is more likely to complement existing query languages rather than replace them. Moreover, AI and machine learning are increasingly being integrated into the internal workings of databases. AI-driven optimizations can enhance query planning, indexing, and configuration tuning, resulting in more efficient and performant database systems. These advancements are paving the way for self-driving databases, systems that can automatically adjust and optimize based on workload patterns without requiring manual intervention. The integration of AI into databases represents a new frontier in database technology, one that will continue to evolve alongside advances in machine learning and natural language processing. However, just as with other innovations, these developments are not replacing the relational model, but are instead enhancing and integrating with it. The core principles of RDBMS, structured data management, SQL querying, and ACID transactions, remain as relevant as ever, even as databases become more intelligent and adaptable. Despite the emergence of new database technologies over the past several decades, the relational database management system has demonstrated remarkable resilience. Each wave of innovation has reinforced the core principles of the relational model, either by being absorbed into it or by failing to displace it. The flexibility, power, and robustness of the relational model have allowed it to continuously evolve, incorporating the best ideas from other technologies. Looking ahead, RDBMS will continue to play a central role in data management. While new technologies will undoubtedly emerge, they are more likely to complement and extend the relational model than replace it. In the world of databases, all roads seem to lead back to RDBMS, and with the integration of AI, these roads are becoming smarter, faster, and more efficient than ever before. If you are interested in discussing your specific data engineering needs, please reach out to us at EQengineered. We look forward to helping you with your data engineering needs.